Good talk, Matt. All right, so we'll go ahead and continue on today. We'll finish up our discussion of processes. Excuse me. A couple of different multi-processing paradigms to look at. And then we'll go into threads, which they're really just a lightweight process, which hopefully you can see the advantage of that since you don't have to copy a whole process. You're just copying the part that's important for execution. We'll do a couple examples with threads, and then that'll be all for today. I'm actually not assigning any homework or labs because the section on threads is really short, so that'll be combined with a later section in this course. But it is important to go over threads right after processes because it makes a lot of sense. All right, communication models. What were these two communication models? Let's see.
Message passing and shared memory.
And shared memory. All right, we're doing great.
Also has to be on our homework.
Well, since it's on there, what's the advantage or disadvantages between these two?
Message passing requires it to go through the kernel, which takes longer.
Okay.
And shared memory requires a larger memory allocation.
And you have to set it up before usually. So.
All right. Yeah, you got to set it before.
Pre-pointed.
Okay. What if these two processes were on different machines?
They
You
cannot
probably
have
want to
shared
use
memory.
a.
They can't.
They can
Oh yeah.
on a third machine.
No, even on wherever you designate the memory is, that's where it's at.
Yeah, and
It's
then
just that one machine's going to take longer to access the memory than the other, but
yeah.
still.
So if they're shared across different machines, when it tries to access the shared memory, it has to go through the kernel, go talk to the other guy, bloop, 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 all the way back.
So then it just becomes message passing.
A very slow form of message passing.
It's slower than message passing.
Oh yeah, because you
Yeah,
have this
that's-
memory, you got to do a translation, go to the kernel has to talk to the other kernel and say, whoa, 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 is it okay to write here, or have we made a change or something, and then it has to update and go back.
And in message passing between two machines,
You just send a message.
they still have to go through the kernel.
You have to go through the kernel, but the kernel does not have to guarantee the coherence of the shared memory
Okay.
between the two machines. Because
So
if you have
it doesn't
shared
talk to the
memory,
other
this is going to be
kernel?
on one machine and on the other.
So it doesn't have to talk to the other kernel?
In message pass, no, you still have to talk to the kernel, but you don't have to maintain cache coherency or memory coherency, which is another problem. So if process B reads from the shared memory on his machine, how does he know A hasn't changed it? So anytime you do writes or whatnot, we got to update everything or make sure everything is consistent.
Oh, so they both have memory allocated on their own machines
Oh yeah, they have to.
as shared memory.
That's one way to implement it. Or the other way is to actually have one of the machines have the shared memory and then copy back and forth, which, yeah. Anyways, shared memory is probably pretty good on a single machine. Not a bad solution, although there are some tricks to it. Message passing is more robust, I would say. All right. So cooperating, we talked about this. Independent, don't affect execution. Cooperating, they affect each other's process. So, all right, independent, they do their own work and ignore each other. Cooperating, they're going to actually interact, usually shared memory or message passing. Why do we do this? Well, it gives 4 reasons, but the main reason, computational speed up. Although convenience has actually become a bigger and bigger thing nowadays as tools for doing this multiprocessing have become really good, or are very mature, I should say, as well. Sure, modularity, but that can be achieved other ways. All right, producer consumer. Have any of y'all dealt with this before?
Yeah.
Ooh.
I don't remember where.
I want to know where.
In message
I
passing.
don't remember.
In message passing.
I think
Reads
somewhere
the
else
message is the
too.
producer, the one that reads the message is the consumer.
Okay, there we go.
I
Right.
thought in data, no, it wasn't data structures.
It's very different.
No, it was operating systems. Never mind.
It's okay, Tyler. That's how life is.
There's the one I was just thinking about. Okay, you produce so many, and then you have to access it. So it had to be this one. Wow.
Okay. All right, yeah. Producer produces some information that's consumed by, well, it doesn't have to be a consumer, but what are more consumers? is usually how it's done. So they have to communicate. What?
What's the problem?
What's a common problem that's producing?
The slide is named the producer-consumer problem.
The problem is, how are we going to implement producer-consumer using processes? How would you implement it? You had one thread that produces information, and everyone else has to consume it somehow.
Very vague.
Smoke signals.
Smoke signals? We get smoke signals?
I don't have
How
enough
many
information
processes
answer
have
your
to consume
question.
it?
In.
All right, sucks.
How many computers are these processes residing on?
M. Good try. Good try. Nice.
Oh my gosh. Because if you produce something and you have an unlimited number of people want to consume.
Oh no, it's not unlimited. It's unbounded.
All right, so if m equals 1,
Did y'all know the difference between unlimited and unbounded? So unlimited means that it goes on ad infinitum. Unbounded means that there is a finite set. We just don't know it yet. That's basically it. Go ahead.
so if m equals 1,
Okay.
shared memory.
All right.
If m is greater than 1, message passing.
Okay.
Well,
If
wait,
m
wait.
equals 0, segfault.
Wait.
You can't actually write your code to throw a seg fault intentionally, which is what makes that funny.
Okay, throw exception.
No, you can just generate a seg fault. You can do that, Steve. You just signal seg fault.
Oh yeah, array size of 1, access.
No.
element
There's a command, a function where you say signal to generate a signal, and you pass it in seg fault, and it'll generate a seg fault on your process and kill it.
Because you got to make sure that every consumer has the opportunity to access that.
Yeah.
And then if you only have the one bit of memory and you're ready to produce something else, you gotta say, hey, well, time's up. If you don't grab it now, I'm putting another product out there.
Okay, so you're going to overwrite the buffer. So
Yeah,
you've started talking about a
I was
buffer.
thinking you didn't have. Now, if you had a lot of storage warehouse, who would you care how many consumers you had?
Performance. Yeah, maybe it's depending. Okay. All right, we have the unbounded buffer, no limit on the size of the buffer, and the bounded buffer. Okay, wow, that was really descriptive. But basically, you're going to talking about, I should say, that there's a buffer where you're sending everything out and the consumers have to grab it from the buffer. Okay, and the slides go through a Java implementation of this. How many of y'all would rather do Java than C?
Boo.
All right, good. We'll stick with C. So your homework will stay in C, which is good. But it's nice to look at least at how Java decided to do it. So they decided to go with a buffer interface, abstract class. So none of this is implementation. It's just a schematic, I guess, for a class. Void insert, so you can insert an item into the buffer, and then you can remove an item from the buffer.
Doesn't have to declare the storage mechanism.
No, this is an interface. So you are then free to implement these two functions however you feel like it. So we had a bounded buffer, implementing buffer. So the bounded buffer is going to implement it. And it looks like buffer size of 5. You have to count number of items in there. Int or n points to the next free position. Notice the data object he chose was an array. It could be other things, but we're going to have a buffer as an array. That's actually pretty common. In is the next position that's free. Out is the next, points to the next full position. Initialize everything to 0. Go ahead and create the buffer with 5 objects, or can point to, well, actually, create the buffer to be 5 object pointers. Oh, it looks like we're going to do insert and remove on the next slide. Great. So insert, well, the count is equal to the buffer size. Count is how many items are in there. So if count is equal to buffer size, the buffer's full. And in this code, we just do nothing. So it just spins.
That's horrible.
It is, isn't it? What should it do instead?
Create a new buffer.
Create a new buffer.
No,
Okay.
Hold on, wait, you're saying which is Well, counting the buffer, do nothing.
Yeah, that's what the semicolon is. So while the buffer is full, is really what this says. Do nothing.
This is for the producer.
No, this is the well, yes, but this is the buffer. This is a bounded buffer. The producer and the consumer are going to use the buffer because the buffer is what the producer and consumer use in between.
Yes, but if it's
Clear the
full,
buffer.
shouldn't a consumer be, if it's
No,
full,
because it's full.
They should clear it.
You should, when in doubt, wipe it out. But the
Right,
consumer
well,
hasn't
the
consumed
consumer hasn't-
it.
The consumer hasn't used it yet, they probably don't need it, they need the newest, latest.
What if the
and greatest.
consumer is just busy and hasn't gotten to it
It
yet?
needs the latest and greatest.
But what if we need to be exact and precise?
Yeah,
You just wanted like,
Archive it.
what if this is a bank, right? And you're doing deposits and withdrawals. You just wanted to maybe only account for the withdrawals and forget the deposits?
Yeah.
I mean,
Except do it in reverse.
you would want it in reverse. But what if you were the bank?
Someone needs to bring this producer-consumer method up to McDonald's in the drive-thru.
Increase the buffer size.
Oh, they get rid of stuff.
All right, let's just say
Sure,
that we can't increase the buffer size. You said this was still a terrible idea, and it is.
Yeah, it's not.
Think about it.
Just get rid
This is
of it.
actually a good question. What should this code do instead?
Force the consumer to take a,
All right.
But you already said it was busy.
Okay, all the consumers are busy, they can't get another object, your buffer is full. What should the producer do besides spinning?
what should the producer do? He should use the
Stop.
object.
You should stop what? Spinning?
Yeah.
And how would that be accomplished inside the kernel?
Just waiting.
So we go to wait. What does that do? You're on the right track, just using different words.
It stops the process.
It allows somebody else to use the CPU.
It's-
There we
Stores
go.
the state.
So basically what should happen here is it should say, well, I can't do anything. OS, go figure out what you can do.
And I'm gonna go smoke a cigar. That's
What?
And that's it. And the program says, and I'm gonna go smoke a cigar while I wait.
Right. In Java, you call system.yield, and that actually tells the OS to schedule it on the back of the process queue, which is a far better solution than this, because it's going to it'll pop back up in time for you to be able to figure out what's going on. Other solutions is called .sleep, passing in 0 seconds, because that will also send it to the back of the scheduling queue as well. So depending on which language you're using, it's either yield or sleep for 0. But that's generally would be a far better solution than do nothing.
But while it's sleeping, it cannot produce anything.
Right. It's going to
So if
sleep.
somebody else came up to the ATM and gave them money, it just disappears.
No, the program's not there. I mean, it's some other program's running.
The OS will reactivate the program.
And now it'll have 2 objects to insert.
Okay. The object is going to freeze no matter what, whether when the buffer is full. That's what this code's doing. What you're thinking of, yeah, you would need a second buffer. But we're just saying we can't increase the buffer size. The consumers are all full. We've reached the capacity of our system, is what I'm saying. What should it do? Yield, because maybe these consumers are also running on the CPU, and maybe we should jump back and let the consumer take over the CPU for a little while, right? But that's not what this code
Get
does.
better consumers.
Yeah, we need better consumers. Always. Common problem in business. All right, the buffer is finally not full. We'll increment the count. We'll put the item into in, and then you increment in. Okay, this is kind of wacky code. What may look wacky for some of y'all? What is this actually doing?
Stuff.
It increments in by 1. And why is it modding it by buffer size?
Because
go
the
back.
buffer size is 5, that would be 0.
Right. So it's going to be a circular buffer. Because once it gets in, it goes back to the beginning. All right, that's insert. How about remove? And this will be called by a consumer. Excuse me. So object item, count to 0. Oh, do nothing. What should it do instead? AKA, if there's nothing to consume, count to 0. It should instead yield. Yeah, it should just yield.
Well, do nothing would still lock out the processor. Wouldn't it? It just
This would
keeps
spin
evaluating
lock
the
it. Yield would say, okay, someone else can do some work. Maybe the producer can go find something for me to do.
So never do a while that does nothing.
Right. call.yield, please, or sleep for 0. It does actually improve the performance of your system. All right, decrement count, get that item, increment out. If you look at that circular thing, return that item that we just grabbed. Okay. Wow. What is a problem with this code? Actually, huge problem.
Besides the one we already said about the count equals 0.
Even, what's a problem? Like, I mean, the whole yield thing is something to improve performance. This is a problem that is far worse. It actually will have your program behave incorrectly. Or set fault. That could happen.
If it's not.
You are
there,
away, you're in a loop, and as long as you keep removing until the count is 0, and then do nothing. Well, what happens if the consumer, and the producer is continuously putting something in, so you keep removing, he keeps producing. That's good.
All right. So here's the question. If there is one consumer, this code's okay. What if there are multiple consumers? What could happen?
Two consumers could try to grab from the buffer at the same position at the same time,
Yes. Why would that be bad?
because only one of them can get it. Or no, because then out would go out +1 and then out +1 again. But they would have both grabbed the same item.
Yep.
Wait, they would both grab it, so the counter would be increased twice, you said? So
Yeah.
you would be,
Yeah, what if you had two consumers, count was nothing, they were both spinning in this while loop, the producer finally produced something, they're both going to decrement count by 2, and then item, they're both going to grab the same item, they're both going to increment out by 1, aka 2, in the total, and then they're both going to work on the same item. Do we want that?
We need to lock the buffer.
We need to lock it. That's right, you gotta lock it. How do you do that in Java?
Lock.
Nope. Good guess though. All right.
No one likes Java.
No one likes Java?
no.
Yeah, Java's not bad.
It's a Java, but-
All right, you add the word synchronized to the top of this function so that only one thread. Operating systems?
Not yet.
Not
At the
yet?
next class, I just can't remember.
Oh, okay. You don't want to talk about OS?
Not particularly.
Oh, I see how it is. All right, well, have a good day.
See ya.
He's got a nice class, he came way early.
Right. He'll be gone for a while. Synchronized up there, what that does is make it so only one thread can execute this function at a time.
And that's handled by the OS? Or the
That's
Java?
handled by Java, which in turn will make it handled by the OS. But it's Java's problem now when you add synchronized, because they use something called monitors, while most of the time people use mutexes. But we'll get to all of that, I believe, in chapter 6 or 7, possibly 8.
Good, I need to learn about consensus.
Mutexes? Oh, it's coming. All right, we just talked about this. Bounded buffer creates an item, calls insert, does all the work. If there's room, insert won't return complete until a spot becomes available. Great. Consumer calls remove, does the work, check if there's an item, remove won't return complete until an item becomes available to return to consumer. It eats the item, haha, i.e. it processes it. All right, good. Any questions on that example? Good. Inter-process communication, that is way too syllabically intensive, so we just say IPC. Mechanism for a process to communicate and to synchronize their actions. All right. Message passing. Inter-process communication, usually called message passing. There are only 2 commands you need. Please keep in mind that there's many more commands that are used in order to improve the performance of IPC. But when it comes down to it, you only need to be able to send and receive. So P and Q wish to communicate to each other? Huh. All right, P and Q, not Alice and Bob. So you got to establish a link between them, exchange messages. All right, can be either physical. You can do it with shared memory or hardware bus, or you can do it logically. That's something inside the kernel that manages it. Hardware bus, Ethernet's another common one. How are the links established? Are we going to answer these, or are we just going to ask the question? Oh, we're just going to answer these. Great. So how are links established? Let's ask this. Who's in charge of establishing these links?
The operating system.
Oh, that was a good one. Can a link be associated with more than two processes?
Yes.
Yeah, if a question ever starts with can, you can pretty much just say yes. Unless it's like the halting problem or something. But otherwise, yes. How many links can there be between every pair of communicating processes?
Yes.
It didn't start with can, it started with how.
And
Sure. Or n minus one. Or how many links can be between every pair? Oh, hold on. Think about this. How many links can be between every pair of communicating processes?
Yeah.
So if you have
know
two
two.
processes, how many links can there be?
Yeah.
You have two processes. How many links can you form?
And
one.
M? Oh, okay. Yeah, one or M. Normally you just want one, but it did ask can, and yeah, you can make as many as you want, although why would you make more than one? Look,
don't know.
we don't know, but the answer was can. So this was a terribly written question. What is the capacity of the link?
depends on the method of the link.
All right, Chris knows how to answer these questions. All right, everyone listen. He knows exactly how to throw the question back at you, which is good because these are terrible questions. It's the size of a message that the link can accommodate, fixed or variable. Oh, you got it. Chris has got it. Depends. Is the link unidirectional or bidirectional?
well, depends.
There. All right, you are catching on. All right.
It's not really.
Although,
That last one's not a
no,
question.
because on this one, you did say that you have to have send and receive, so it has to be bidirectional.
Actually, is a link unidirectional or bidirectional? Yes, it has to be one of those two.
No, because you can have two links, one for receive, one for
Right?
send.
Yeah, you know, the way you read that one, actually, this question will determine how you answer it, right? Because yes is actually a viable answer to that one. Man, all right.
Oh, but they explain it down at the bottom.
Yeah, okay, not really right. They're just choices with advantages and disadvantages, right? All right. Process must name each other explicitly. Yeah, each process needs to know who he's talking to. So you send to P with the message, and then P will say, I received from Q this message. Let's see. Links are
How do you
established.
receive a message you haven't received yet. Receive from Q this message, but he hasn't gotten that message yet.
Oh, then if you are trying to receive a message from Q and Q has not sent it, what are you doing? You are blanking for that message. Waiting, yeah.
But you don't know what that message is.
Yeah, you do. Oh, you have to. If you
Okay.
don't, your process
Send
dies.
to P
Mm-hmm.
1.
An integer?
Receive
Whoa! Stop!
one, But I haven't received one yet.
Stop! Whoa! One what? One integer? A
Just
double?
an arbitrary
A
message.
pointer to a struct?
Just an arbitrary message.
No. You
I
have
need
to be.
I title it
No.
one.
You got to be explicit. An integer?
Sure. I did.
Okay. Send.
Send to
P,
P,
an integer.
the integer 1.
Okay.
Receive from Q, the integer 1.
No, just receive from Q an integer.
An integer. Okay. But you have to be expecting an integer.
Yes.
Okay.
Otherwise, this is all a no-go.
That was my point. You'd have to know that they were sending.
Yes, that's what the word explicitly means. You have to explicitly say everything that's happening.
Well, no, but you can set up a while loop while no message is received. Keep running receive queue, waiting for a message to come.
Yeah, but how do you know what the message is? How do you know a message is an integer or a double or a float or a character array or a giant record or, random
Any or
object?
all,
Well, how do you know when the message ends?
because it's got a terminating line.
How do you know the
All
terminating
messages
line?
are strings, and we have to interpret them.
Oh, okay, so you're going to say everything's, which is the Unix philosophy. That would actually simplify things a lot. But what if you have to communicate with that horrible operating system known as Windows?
We don't.
So basically, in the beginning, you have to send all the parameters. of the
Well,
message.
both processes the one that's sending and receiving, need to know exactly what is being sent and what is being received.
Is that established by the link?
That is established by you writing the program correctly.
For both programs.
Yes, for both programs.
Or reading the API of the other program correctly.
Or you use an API that does a lot of this work for you, and therefore you don't have to worry about a lot of it.
As long as the other one's using the same API.
Well, you make well, obviously, yes.
That's the whole reason to make that.
Yes. All right. A link can be unidirectional, but it's usually bidirectional. All right, great. Indirect communication. So this is what you were thinking of with mailboxes. Oh, we have already talked about one of these, or I know you've experienced one of these. Messages are directed and received from mailboxes, also referred to as ports. Okay, that's cute. Each mailbox has a unique ID. Processes communicate only if they share a mailbox. Link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication. Link may be unidirectional or bidirectional. What's an example of this?
Shared map.
Yeah, we could call it shared memory. Good answer. Good answer. What's another one? Although, no, it's not, because shared memory is not message passing. So I take that back. Take back my answer.
Well, that doesn't, there's nothing in there.
When you have two computers and they go through the internet and they have to hook up to each other, the handshaking process.
Oh, so socket and network communication, that could be a mailbox. Even on your machine, though, in Linux under Bash, what would be an example?
Oh,
Piping.
Piping. Yeah, piping is a good example here. Which can be unidirectional or bidirectional, depending on how you set it up. So you have to create the mailbox, the pipe, send and receive messages through the mailbox, the pipe, and then destroy the mailbox, the pipe, when the process is done. In Linux, the pipe, it's destroyed when EOF end of file is sent. So it's actually a pretty standard way of doing it because you're just sending text, right? Everything's just text. Let's call it a day. Yeah. Everything's just... Oh my goodness. All right. Mailbox sharing. P1, P2, and P3 share mailbox A. P1 sends, P2 and P3 receive. Who gets the message? Should both of them get the message?
Depends on what the program's doing.
Okay, there we go. Yep.
If you need the sign and cosign of what you've sent, and one process does the sign, the other one does the cosign, they both should get it.
I don't exactly understand what they're asking here. It depends on how you set it up. Although if it's a mailbox, you want both of them to get it, technically. So you want the link to be associated with most two processes, one process at a time to execute or receive operation. If you only want one of them to do it. Allow the system to select arbitrary receiver, sender is notified when who the receiver was. All right. So in this situation, it would only do one.
In other
Or
words,
the mailbox keeps track of who receives it and who's supposed to.
Yeah, you could do that too.
And it only destroys the message once all the people that are supposed to receive it have taken it.
There you go. Sounds complicated. All right, synchronization. Why is synchronization good?
Because everybody works together.
Okay, everyone works together. Blocking is considered a synchronization. You can do a blocking send where the sender blocks until the message has been received. Naturally, a blocking receive is also the receiver blocks until it receives the message. So what would non-blocking be? Oh wait, I can't hide the text.
Especially with two of them.
I know, we have definitely made this harder on my life. So you can do a non-blocking send where you just send it and you don't wait for them to receive it and go on. And that probably makes a lot of sense. You know, you just send it off and you don't really care. Maybe you need to do something else for a while. You got better things to do than wait for them to acknowledge the receipt. How about a non-blocking receive? Why would we do this?
In case you mess up sending it.
In case you don't, in case the code that you're running doesn't necessarily need the message just modifies it.
Okay, yeah. Yeah, maybe the message would modify it, so if it hasn't received anything, go on. Also, if you're trying to receive from multiple producers and you want to check, you want to do something once you receive something from a producer, you're going to go and do non-blocking receives from all of them. And if didn't receive, oh, received something, do something, then go through your list again.
I've lost the.
Sure.
I understand blocking is consistency here, so blocking send. I understand that it has to send a block from the message you receive. So basically, the sender's not going to send anything.
What happens is once the sender sends something, he waits. That function send waits until someone has received that message,
Right.
and once he's received acknowledgement of receipt, then he continues.
And blocking receiver block until a message is available. So the receiver is
Waiting. until
Waiting.
The message is in the mailbox.
Yeah, in the mailbox, and it's a full. It's fully in the mailbox, and then they receive it.
okay. This could tie up the CPU. Though.
Yes. Well, in the correct implementations, we go back to that whole yield where it
Oh,
actually is,
right.
it sends it back and it's scheduled appropriately. It'll actually be in the interrupt queue, waiting for a certain interrupt to come. And then once the interrupt comes saying, hey, look, you have your information, then it'll be put back on the regulars.
And the non-blocking, because this is considered secret, is basically you're accessing it at different times or whatever.
It sends it. If you're sending, it makes sense. It just spits it out. Hey, you need to go.
Don't care if somebody received it or not.
No, but it's been
Go on
sent.
your way.
It's been sent, and you go on. That one's pretty intuitive, I
Oh,
think.
okay.
A
So
lot of
the
people
last
understand
one-
why. But the last one's the one that people don't always understand why we would have non-blocking receive.
Once again, so the non-blocking receive has the receiver. It's sitting there. It says receives a valid message or a null. So basically,
It's either received a message or it hasn't. If it has not, it immediately returns saying, I have no message.
Okay, so basically, I checked the mailbox. Nothing's there. I'm on my way doing something else.
You got it.
Okay.
Very common reason for that is if you have multiple producers, you got to check the mailbox of each producer, right? So nothing in this one, nothing in this one, oh, someone has something here, now I'll work there. So you can kind of go around
Keep
checking.
pulling the-
Yeah, pulling all of them is a common thing to do here. All right. We good? Thank you, Matt. Buffering. Queue of message attached to the link. Implement one of three ways. Zero capacity. No. So that's the. Namely, if you're going to have a buffer and there's a. Yeah. If it's a capacity of 0, it basically becomes a blocking send because you have to wait till it's actually the whole thing has been sent before you can do anything. You have a capacity finite length of in, so you can put so many messages in your buffer and wait until it's full. Unbounded means, well, at least it seems like infinite length. The sender never waits. Which one of these three do you think is implemented?
Bound capacity.
Yeah, bound capacity, because you have to have a bounded capacity at some point. Although it's usually a pretty good buffer, so the link is usually not full. All right, POSIX. What does POSIX stand for? All right, the P is portable. What do you?
Operating system.
All right, you got it.
9.
Nice. And for yeah, I forgot what the last two stood for. But the idea is it's an interface between it's basically a standard operating system interface for doing different things.
Exchange.
Yeah, it's some type of information exchange or something. I can't remember.
The I is interface.
You asked us a
Interface.
question that you didn't know the answer to.
Well, why
What
wouldn't
would you ask a question?
Well, thank you, John. See, come on, man.
Schmemkit.
Yeah, Schmingit. Share memory get schmick. And then you can get shared memory. This is another way to do shared memory. I showed you mmap, which I think is a little cleaner, or at least easier to use. And then when done, you detach it by shared memory destroy, or detach actually. Good old mock that no one actually cares about anymore, but hey, look, they did implement send and receive and RPC. What's RPC?
Remote process call.
Yeah, perfect. Remote procedure call. Close.
No, you said perfect. You can't take it back now.
All right, then there's IPC of Windows. Of course, Windows has to be different than everyone else. Local procedure call only works between processes on the same system. Why they would make that choice, I don't know. Uses ports, so you're going to have local procedure calls, but you're going to use ports, which would be the whole point of using a port is so that you can do it remotely. All right, anyways. To establish communication channels. Sorry, I hope no one's offended by my bias. Actually, I don't really care. Communication works as follows. The client opens and handles subsystem object, sends connection, okay, et cetera, et cetera. Windows does it internally with ports. And look, it gives us the nice flow graph.
Wait, that's two different stuff.
No, IPC, Windows XP, local LPC, and Windows XP. The client and the server are the same machine. Yeah, that's what's confusing here. Even though they use the word port, which implies this could be over Ethernet, but whatever, that's just silliness. Client port, and then, all right, fine, it talks, and then eventually gets a shared object. All right, as you know, I'm not going to quiz you over this. All right, how many of you have done sockets before? Oh, no socket program. All right, maybe we'll have to have a socket programming lab. RPC and RMI. So a socket is definitely an endpoint for communication. So here's a great example. Socket IP address. You all know what IP addresses are from network. Okay, good. All right. Whew. You know what a port is?
Yes.
Oh man, we're doing great. Perfect. So that's an IP address with a port. Usually the way this does is it communicates, you create a socket which is bounded to your internal IP address, and that socket's also bounded to a port. And then that socket is when you have two sockets, one on each machine, aka IP address and a port, they communicate over the socket. And you have to configure the socket to be, if you want it to be TCP, UDP, or anything else, ICMP, et cetera, ESP. Yeah, so socket communication, host, .20. The socket's also .20 on this port. Web server's .8. Notice that his port is .80, and that guy is 1625. That's because when you want to try and contact the server, you got to go to port 80, so the socket has to be on port 80. But the server needs to know how to communicate back. So you actually need to open a socket on your machine to tell the server where to send the information back. Any of that confusing? Not yet? We'll get to better examples later, but this is a good high level. RPC, the whole point of this is to call a remote procedure. You might as well just replace the word procedure with function. And I think this will all make perfect sense because it's basically the same thing. You literally are, you're on one machine, you want to call a function on a server, the server runs your function and returns your result. That's pretty much all you're doing here. Hey, look, nice, good flow drive. User calls kernel to send RPC to X. The kernel packages it up. Why would the kernel need to package this? Well, okay, packages up. We'll talk about that in a moment. Opens the socket, server gets it, looks up the answer, replies to the client with port P. The kernel places port P in the RPC message saying, all right, so we've established this connection, we're going to do it over this port. Now it sends the RPC over the port. The daemon, or daemon, however you prefer to pronounce that, receives a message, processes the request with the RPC, and then returns the answer.
And packaging, like just basically your protocols.
It's marshalling. Yeah. Have we talked? We will talk about marshalling in the last slide of this presentation, which is coming up after this one. Remote method invocation. So this in Java is a mechanism similar to RPC. Sure, we can call it similar. It's basically the same thing. Where one machine invokes a method on a remote object. Does that sound like the same thing?
Yeah.
Yeah, it's basically the same thing. Except for now you're doing it within the two Java JVMs. It does a lot of the heavy lifting for you. So instead of having to do all of this, you just set up RMI and you're basically good. good to go. All right, marshaling. Last important question, which I believe is on your homework. Is it, Matt?
I don't know.
You don't know?
I'm gonna bet.
We're talking about which,
All right.
this one did not have.
So if we have a client and we have a remote object or a server, can the client just say, hey, I want you to call this function at this address with this data? Well, okay, can it? Yes. Is that always going to work out well?
No, it's for a reason.
No is the inferred answer. So I'm definitely leading you in this direction. What problems could occur?
Sadness.
Sadness, right? So the user of the program could start crying.
Because you're talking it's only a chapter 3 homework.
Yeah, it's still chapter 3.
Okay, well, you only given us 1 and 2.
I'm doing chapter 3.
Oh, really? Oh, okay, I only got the Blackboard, then I did.
Oh, remind me to update Blackboard then.
Oh, okay.
When we're done.
When is 3 due then?
When is 3 due? Probably Monday?
Tuesday.
Tuesday.
Oh, exactly, okay.
I'll update it. Tell me on the time. All right. So client is one machine, server is another machine. What are some issues that, and they're connected via Ethernet, what are some issues that could occur when doing RPC?
The link is destroyed.
The link is just right. Good point. Something else? Let's say the link is just fine.
You don't
Use
want
the data.
the client to be able to make the server do whatever the client says.
Okay, yeah, so the server, but that's, yeah, so the server has to do some security. That's a good point. That one day we'll get to marshaling. Good, I mean, that's good. That's definitely something that the server has to do. What else could occur?
The implementation is different.
Implementation is different. All right. What parts could be implemented differently?
Every part.
Every part.
The PIDs.
All right. List some parts that could be
So-
different then.
So the marshaling involves, okay, saying, here's our information, here's the format it's coming in, and this is the format I want it coming back to me.
You're on the right track.
So like,
Not quite there yet. Well, all right. What if the client is an x86 machine running Linux and the server is BSD on an ARM processor for some reason?
And we're sending machine code.
No.
Yeah,
We're saying-
sending again.
We are sending, I want you to call this function with this data.
The data might be different types, kinda.
Yes. What if the client is big Indian and the server is little Indian?
Sadness.
You need to marshal it, aka you need to come up with a standard way to organize that data so the two can communicate. Furthermore, your network communication may also be different. It may be a third data format. So there's actually 3 data formats that could occur, but they all need to agree on something. Usually the way it's agreed on is whatever the network does. So the client is going to marshal its data so that it adheres to the network standard. So an integer is formatted, I believe, a little or big Indian, and then 32 bits for an integer. Same thing, long of 64. It'll be organized, and there's also a byte ordering that's important because you have to order it in the correct number of bytes. So that's what the client does. It marshals it to the link. Obviously, the server, once it receives the marshal data, what does it need to do?
change.
Yeah, so it changes it back. So it unmarshals it, does what it needs to do, marshals it again, sends it back, and the client unmarshals it when it's over there. So there's a lot of different, things that can happen due to the fact of how data is stored on different machines. Any questions about marshaling? Hopefully we'll see a little more of this later. The end? End of chapter 3. All right. How was chapter 3? Long?
Yeah.
Kind of long.